and possibly say, I don't need the utility, I'm going to be on my own, and they stop being a customer of the utility. And as more of those happen, of course, revenues of the utility would drop. And as revenues drop, the utility would need to raise prices to make up for that lost revenue. But as they raise prices, more customers would drop, and that's what's called the death spiral. So we have to be very sensitive to that. And you know, the question is, would residential customers truly feel self-sufficient if you had your own generation? I mean, I personally, even if I had my own rooftop solar panels, would still want a connection to the utility. But it's something to be sensitive to. So let's look at what we mean by smart grid solutions. These are 6 that we began developing about 6 years ago, and it was based on the strongest business cases for customers. And you know, one is asset optimization, which today is transformer monitoring and diagnostics. 2 is demand optimization. 3 is smart metering and two-way communications. 4 would be the distribution part of the utility, optimizing that. 5 would be the transmission part of the utility, and 6 would be looking at the workforce and also looking at engineering design optimization. The reason we need to focus on the workforce is that in our industry, in the next 5 years, 40% of the engineers and 60% of the executives will be retiring. It's very unique in an industry. It's huge. So, you know, one aspect of that for young professionals like all of you is that there's tremendous opportunities in the power and energy field, and it'll just continue to grow because we'll have a lot of retirements of very experienced folks and still have a lot of work to be done, so that the demand is increasing for particularly well-qualified young professionals, and the supply is just very not close to meeting the demand. So that demand will continue to grow, and we really need more and more young professionals that have both, you know, some work experience in the field as well as the academic background too. So let's take a look at each of these from the point of view of a technology roadmap. And you know, when I talked about an integrated solution, a set of technology components that all work together, this is visually what I mean. Let's just take an example here. Let's take the light blue boxes. That's optimizing the distribution part of the grid. If you look in the office in the upper left, the 4 blue boxes near the top are all software applications. In fact, the first one, FDIR, is the one I mentioned, fault detection, isolation, restoration. The one next to it is integrated volt-var control that we talked about. Then the next level of blue boxes down are systems, the distribution management system and the outage management system. Then if we go in the substation, lower left, we have the station controller, hardware and firmware, applications, the logic that can run on top of that, and this is what I mentioned about distributing the intelligence. So we put some intelligence down at the substation level. And then to the right is the feeders. And this would be switches and breakers. Downstream of the substation on the feeders, we need switches and breakers to support fault detection, isolation, restoration. Because the way we isolate the faulted segment of a feeder is opening up a sectionalizing device or a switch on either side of that faulted segment, on either side of a fault. And then volt-var devices would be things like capacitor banks, voltage regulators on the feeder, and we need those to support the integrated volt-var control application. But just take a look at all those blue boxes. Think of those being from a number of different vendors, and they all have to interoperate successfully. Okay, so standards are a must. And so, you know, people had asked me after Hurricane Sandy, with different media interviews, how can a utility best prepare itself for an extreme weather event? And I said, well, there's 5 key components that they need to invest in. One is smart meters, 2 is what we call AMI, Automated Metering Infrastructure. That's the two-way communications with the smart meters. 3 would be a Geographic Information System. 4 would be the Outage Management System, and 5 is a Distribution Management System. So each of those components by itself has value, and each of those would be a blue box, you know, on the previous slide. But the greater value is when we integrate these together. That's so much more value to the organization. And some examples are meter readings from smart meters, but also voltage from smart meters going into the distribution management system. What's the voltage along the feeder, for instance? What's the voltage at the end of the feeder? And the reason we need to know that, in the United States, we're required by law through a standard that the voltage at the customer site, where the electricity is delivered, must be within 114 to 126 volts. 120 volts plus or minus 5%. So certain meters at the ends of long feeders give us that information. And also the last gasp communication. So when electricity is lost, there's an outage, there's enough energy left in a smart meter to make one last communication to the utility. We call that last gasp communication. It says, hey, I just lost power, and this is the time it occurred. And we want to make sure that gets to the outage management system. The Geographic Information System, the GIS, is the reference system for the network model for both the OMS and DMS. We also want to get the DMS is whenever a circuit breaker or a feeder breaker changes state, like goes from closed to open, that status change, the DMS knows that within a couple seconds. And we need to get that information over to the outage management system because the OMS knows which customers are connected to that feeder. And if OMS knows that feeder now was de-energized at a certain time, OMS knows exactly which customers are affected by that. Okay? And then lastly, with customers, of course, they've all, you know, some of them will call in when their electricity's out, but what we're doing now is empowering customers with social media to send tweets to the utility. And it's not unusual for the utility to have your hashtag for Twitter in your customer account. So when they receive a tweet from you, they know exactly who it came from. Okay, things like that. So at GE, we did a survey in August. We announced the results. And one question of utility customers was, what's your preferred way of interacting with your utility? And 70% said they prefer to interact through digital social media, through digital means. Okay. So I talked about standards. And some background here. In 2009, 2007 first, there was federal legislation that made NIST, National Institute of Standards and Technology, the overall coordinator for smart grid standards. And in 2009, they received stimulus funds of $12 million to do the work. So at the end of 2009, there was elections for what was called a Smart Grid Interoperability Panel, or SGIP, to do the work that NIST was tasked to do with the legislation. And at that time, I said that I wanted to be considered for election on the SGIP board. And I got elected to the board, and then in early 2010, the board elected me to be the chairman of the board, which I've been ever since. So right now we have 200 organizations worldwide all working together on smart grid standards. The left graphic here is an industry standard. It's a conceptual reference model for smart grid that we developed in 2010. So think about if you had, if someone gave you a sheet of paper and said, draw all of smart grid on a sheet of paper, what would it look like? And you can see 7 domains here that are interconnected with, see the blue lines. We say at GE that smart grid goes from turbine to toaster. And that's a wide landscape from power plant to customer. And this is a good reflection of it at a high level here with the 7 domains. Now there's a number of existing standards, and what's important here is sifting through all the existing standards and say, what are the most important industry standards for smart grid? And on this slide I show the 16 most important standards for smart grid. So if you're doing any project, developing a product, or anything involved with power system automation, you need to have at least one or more of these standards included, or I guarantee you won't be successful. And the nice thing is we've converged worldwide on just a small group of standards. At the top here, control center to control center, today there's one worldwide standard on how utilities exchange information with other utilities, or within the utility, how different SCADA systems, supervisory control and data acquisition systems, will exchange information with each other. And it's called ICCP, which is an IEC 870-6 standard. And ICCP means Inter-Control Center Communications Protocol. From the control center down to the field equipment, there's really two standards that are used. One is, in North America, it's DNP3, which is Distributed Network Protocol 3. It's now has an IEEE designation of 1815. And then the other is 870-5 with European suppliers. 101 is serial communications, 104 is network, and 103 is for protection devices. Then if we get in the substation with the field equipment, you know, the one worldwide standard there is IEC 61850. And then we also use a lot of DNP3 with substation and feeder devices. So we've converged on a very small number of standards. But we also have to take into account the trend here of the Internet of Things. It's really 3 things being brought together: intelligent machines, which is leveraging technology and communication to cost-effectively connect machines. 2 is big data and analytics. It's the power of big data. We talked about that in the beginning. Big analytics, you know, how do we analyze the data? Can we analyze it in new ways to provide new value propositions? And then people. So connecting people, no matter where they are, at any way you can, at any time, for intelligent operations. And there's tremendous savings there, potential savings. For the first 1% annual savings in the energy field would be about $300 billion over 15 years. So from a standards point of view, I mentioned in 2009 was formed the SGIP. In 2013, we took it from a government-funded model to a member-funded model, which is much more sustainable for the long term. So for about 2 years now, we have members that pay dues, and it's a member-funded model. This is what we do. You know, what are the gaps in standards that we need to write a new standard? Let's accelerate those that have to be developed. Look at standard testing and certification requirements and global harmonization of standards, not just U.S. but across the world. And we have 3 areas of activity here. In the dark blue is the domain expert work groups in different areas. These are visionary strategy groups. They'll look ahead and say, hey, it looks like there's going to be a gap here. We need to write a new standard. In the middle in light green are the new standards being written. So we call these priority action plans. We identified a gap, and this is the work being done. Then on the right in light blue is the standing member committees on architecture, cybersecurity, implementation methods, and testing and certification. So this is some new work efforts. One is on IEC 61850, testing profiles, PAP 23, the PAP is Priority Action Plan. 24 is a new work effort on microgrid operational interfaces. It's just kicked off a week ago. And then we publish utility case studies about every 2 months of the experiences of a utility in implementing technology with certain standards implemented. Okay? It's a great way to share information in the industry with what particular utility had done. And this is the website, www.sgip.org. A lot of information on the website as well as membership information. So let's look at some examples of deployments. AEP is the second largest utility in the United States, 5 million customers, operates in 11 states, and did a number of projects with them and added technology, systems in the upper left there, several distribution management systems, outage management, monitoring and diagnostics. Then in the substation, station controller, we distributed intelligence into fault detection, isolation, restoration, and coordinated VOLVAR control at the substation level. Then you had transformer monitoring and diagnostics at the transformers in the substations, smart metering for both residential and commercial industrial customers, and smart controllers on the feeders, okay, to support, as we talked about before, fault detection, isolation, restoration, and VOLVAR control. And what we looked at 6 solutions, and so with this utility, it's implementing technology in 3 of the 6 solutions: demand optimization, distribution optimization, and asset optimization. A very challenging project has been the Maui Smart Grid project. Very ambitious renewable targets by the state of Hawaii, reducing peak load by 15%, but also handling the intermittency of the wind farms that are being installed. So a lot of technology was deployed. This is an idea of implementing a brand new DMS, the applications on the DMS for things like VOLVAR control, demand management, managing the wind plant, distributed resources, and home energy management. So this is challenging from the point of view of an islanded power system. Is much more volatile anyway because it has no ties to any other utility. So the advantage of the utilities in the 48 states that are all interconnected is that you have support from your neighboring utilities through your tie lines. Then we looked at Energy Smart Miami. This was a city-scale project with a lot of partnerships with other companies like Cisco and Silver Springs, as well as Florida Power and Light, the local utility, and the city of Miami. About 1 million customers and a number of different smart grid solutions deployed, including, for all of Florida Power and Light, 4.5 million smart meters that were deployed. And then just looking at cities in general, it's a good test bed because of city-scale projects is larger than, say, 2 substations and feeders, like a small pilot project. So the bigger the scale of the deployment in a project, the better test of the technology, particularly as you scale the technology across more of the system. You want to make sure the performance doesn't degrade. And so a small pilot project doesn't do that real well, but more of a city-scale project is a better test. Okay, lessons learned. So we learned that the technology components, in many cases, when we first deployed them, were not as mature as thought, and there was field re-engineering and upgrading that was needed. Also, that integration and interoperability is key, and it'll only be successful with standards and open architecture. Third is you can't do enough testing in the factory or in the office before you go out in the field. And the other thing with testing is end-to-end testing is important. Next is coordinating multiple suppliers of equipment. And And having really good project management and making sure the project manager has the authority over the multiple disciplines that are involved in the project, not just the responsibility